Greetings and welcome back. In previous videos we've been looking at how we can turn a C double bond O into two C double bond ORs, or a C double bond O into a C double bond N. That was an imine. In this video we're going to be looking at how we can turn a C double bond O into a C double bond C. And this is going to be called the Wittig reaction. It is spelled Wittig, but it is a German name, therefore it's pronounced Wittig. I'm going to do this reaction a little bit in reverse. That is to say, we're going to start by looking at the way that we form that C double bond C, and then we're going to look at afterwards on the next slide how we create these reagents. So overall, what we're going to do is start with an alkyl halide and combine it with a carbonyl to create a new C double bonded to C, where this part right here of the carbonyl becomes one of the sides of this, and the alkyl halide's carbon becomes the other side. When we look at these two things, you can't put an electrophile together with an electrophile and make a new carbon bond, so we really need to be turning one of these guys into a nucleophile. And in the Wittig reaction, you turn the alkyl halide into something that looks like this. We'll call it PPH3 for the moment, which is an ylide, Y-L-I-D-E. You can see that this carbon right here with the C minus is definitely a nucleophile. C minuses are very hard to achieve, but this is achieved through resonance, and that's why this is stable enough to exist. It makes a resonance structure in which we would have a C double bond P, which is very odd, but I will show you what this looks like in just a second. So this is the ylide. It is itself the carbon nucleophile at that spot right there. PH stands for phenyl, so really what this guy is a C double bond to P, and that phosphorus makes 3 bonds to benzene rings. So you can probably see why we shorthand this into phenyl, because it becomes very cumbersome to draw this guy as a large molecule. I haven't indicated anything at the end of these bonds because really they can be anything. It works well if maybe one of these is an R and the other one's an H, but when it comes to the carbonyl it doesn't really matter. Alright, so that is the ylide, and that is the carbon nucleophile that we make. So we'll focus first on how these guys get together, and then we'll go back in time and talk about how to make the ylide. Alright, so let me shrink these guys up a little bit. Put that over there. Alright, so in terms of that ylide, you have the reactive species of a C minus attached to that PPH3 plus. And when we put that together with a carbonyl, clearly the C minus is a nucleophile. We'll attack that carbonyl, kicking electrons up to the O. That would give us a carbon with a PPH3 attached. So 3 phenyl groups. And that phosphorus would have a plus charge. And that would be right next to a carbon with an O minus. So negative charges and positive charges are attracted to each other, and indeed this O would make a bond to that phosphorus, making them both neutral. So that would give us a square, which is very unstable, or a 4-membered ring, I suppose I should say. And therefore, what this guy is going to do is it's going to break. And how that happens is that we effectively make a P double bond O. These electrons become a C double bond C. And so the net result of this reaction overall is that we are making a C double bond C, in which this chunk right here, which is attached to the ylide, becomes this part right here, which is still attached to the phosphorus, and ends up making a double bond to the other carbon. The aldehyde or ketone, which was this carbon chunk right here, is bound after that nucleophile-electrophile reaction, goes into that square, loses its oxygen, and then ends up part of that C double bond C. Let's go into a specific example. If I started off with this 4-carbon ylide right here, ppH3 with a plus charge, a C minus right there, and reacted it with cyclohexanone, the C minus right here would end up attaching to the carbon in the carbonyl, and if you look at what's happening overall, I would lose my double bond O, and I would lose my ppH3, and I would end up making a new double bond between the carbon that was the nucleophile and the carbon that was the electrophile. And therefore, I would have my 4-carbon chunk, which would then have a new double bond to my 6-carbon ring. So you can see that in the product, this is the carbon that was the nucleophile in the ylide, and this is the carbon that was was the electrophile in the carbonyl. As a side reactant, or I guess a byproduct, I would generate this thing, which is often written as this as well. But that's kind of beside the point. The carbon-containing functional group that I created has a new carbon bond between what was a C double bond O and what was the ylide. So let's try an example of this before we move on. We saw on the previous slide how we could react an ylide as a nucleophile with a carbonyl carbon to create a new C double bond C, which is a new alkene. Let's look right now at how we go about making an ylide. Ylides, as I mentioned at the very beginning, are created from alkyl halides. So the starting material, and in this case I'll use benzyl bromide or a benzene CH2Br, and we react this in 2 steps. First with triphenylphosphine, or ppH3, and the second step with a very strong base, and we'll usually use N-butyllithium, which is a very, very strong base. In the first step, that phosphorus, which is a better nucleophile than nitrogen because it's larger and more polarizable, can share its electrons with the alkyl halide, kicking off the leaving group and creating a carbon attached to ppH3. At this point, the phosphorus that shared its electron went from being neutral to positive. But the carbon right here is not quite an ylide because this carbon is just neutral. However, because I have a P right here, this phosphorus with a plus charge is effectively an electrophile. Therefore, the carbon next door is slightly acidic. So this is basically an alpha carbon. It's not right next to a carbonyl, but it is definitely right next to something that is somewhat electrophilic. So I can add a very strong base, in this case effectively a C minus, which will pull that hydrogen off and give me a new C minus. The one up here is not stabilized at all. This one down here, the C minus I'm creating, would be stabilized through resonance. So this would give me, in this case, this benzene ring attached to a CH with a lone pair and a minus charge, which then would have a P with a positive charge next door. This would have resonance, which of course would just be, I'll do this in pink, would share those electrons over there, making a 5th bond to phosphorus, but phosphorus is in the 3rd row and can handle a 5th bond. However, this pi bond that we can create through this resonance structure is not very stable. So even though the ylide has a neutral resonance structure, this resonance structure right here seems to be more stable, but realistically this C double bond P, because this carbon has a relatively small 2p orbital and this phosphorus has a relatively large 3p orbital, they don't make very stable pi bonds, and therefore it actually prefers to be kind of in this conformation right here. Regardless, that C minus is significantly more reactive, so therefore it reacts just like this guy. So that's how we make an ylide. Let's try one example of that, and then we'll move into putting it all together. Overall, the Wittig reaction starts with an alkyl halide, adds triphenylphosphine in the first step, N-butyl lithium in the second step, or NBULI, just normal butyl attached to lithium, and in the third step would add the carbonyl for the ylide to react with. So what I'd like you to try is to work through those one step at a time. So in the first two steps, reacting with the triphenylphosphine and the butyl lithium, you would make the ylide and then react the ylide with this specific ketone and see what product you'll get. All right, so let's work through this together. In the first step, the triphenylphosphine would add to that carbon and kick off the bromine, giving me PPH3 with a plus charge. In the second step, I would pull a hydrogen off of that alpha carbon using my N-butyl lithium, creating my actual ylide. This would be the C- right next to the PPH3+. This is stabilized through the resonance structure, but the resonance structure is not the reactive one. Therefore, let's go from here. The C- would attack that carbonyl, which would create my new carbon-carbon bond. And I'll stick my PPH3 up here, which will be right next to my C- that I've created by attacking the carbonyl. And then you might remember that what will happen is we're going to end up making a new carbon-carbon double bond between my ylide and my carbonyl, meaning that overall I'm going to take this carbon chunk right here and this carbon chunk right here, kicking off the triphenylphosphine, kicking off the oxygen, giving them a bond together, and making a brand new alkene. Therefore, my final overall product would look like this right here. So it's worth counting your carbons and comparing them. In my pink chunk that was my carbonyl, I had 3 carbons followed by a benzene ring, which I have here, 1, 2, 3. And in my purple chunk, I had 4 carbons, 1, 2, 3, 4, and I have those carbons still. So therefore, all the carbons are accounted for, and we have used the ylide reaction, or excuse me, the Wittig reaction, to make an ylide, combine it with a carbonyl, and make a brand new alkene. Thank you very much, and I will see you in class.